Momentum, work, power, energy, multiple choice questions. Question 1. Two balls of masses m and 2m are dropped simultaneously from the same height above the ground. Ignore air resistance. When the balls strike the ground, which of the following physical quantities will be the same for both balls? So if you look at A, the weight definitely won't be the same since the weight is calculated using their masses. Okay, option B, their velocities. Yes, their velocities would actually be the same. They're falling the same distance, so therefore their velocity would be the same at the end, because when you dropped and there's no air resistance, so in other words, you're falling in a vacuum, if you dropped, and drop means velocity, initial velocity at 0, that means that every second your speed is increasing by 9.8 meters per second. So after the same amount of time or same distance, they would have exactly the same speed. So it's in fact B, the velocity would be the same after they fall in the same distance. Momentum would not be the same since their masses are different. Okay, even though their velocity might be the same, because their masses are different, they will actually have a different momentum. And the kinetic energy also won't be the same. Again, their masses are different, so therefore they can't have the same kinetic energy when they reach the ground. Question 2. The graph below shows the momentum of an object, how it changes with time. So when you get questions with graphs, you have to ask yourself, what can you actually calculate from that graph? So if you look at this one, it's a change in momentum on the y-axis, and it's a change in time on the x-axis. When you work out the change in y but change in x, you're working out the gradient. So we need to ask ourselves, does the gradient give me something useful? And sometimes you need to check if we'll always check both. Is it the area under the graph that gives me something useful? So the area under this graph would be P times by delta T. Okay, so you can scan your data sheet and see which of these two give you something. Look, sometimes the gradient gives you something, and sometimes the area also gives you something, and sometimes it's just the gradient or just the area. It's up to you to go to the data sheet and check if these things give me something useful. So P times delta T, there's no formula that gives me anything useful, so I'm not going to consider the area under the graph. However, delta P over delta T, if you look at your impulse formula, if I manipulate it and I write delta P over delta T, that actually gives me my force. So the question, if they were nicer, would have just said the gradient of the graph represents the force, but it's up to us to figure that out. So it says during one of the following time intervals, measured in seconds, is the net force acting the greatest. So during which interval, sorry. So if you look at it, you're basically just looking at which one has the steepest gradient. Okay, so you can see from the graph that your steepest gradient is actually from 3 to 4 seconds. Okay, you can work out your gradient if you're not sure. Okay, just to save time, we're actually just going to look at the steepness, and this one's actually the steepest, so it is in fact option D. But your job in a graph question is to figure out, am I looking at the gradient of the graph? In other words, does the gradient of the graph represent something, or am I looking at the area under the graph? In this case, the area didn't give me anything, but the gradient did give me the force. Question 3. A ball is dropped from a height above a floor. The ball makes an elastic collision, which is crucial. So highlight words like that. We'll highlight words like constant velocity, elastic collision, released, which means something is initial velocity is 0. So it says it has an elastic collision with the floor at time t0 and bounces vertically upwards. So it's dropped, which means VI is 0. It then bounces up, and the collision with the floor is elastic. And if a collision is elastic, that means that the energy is conserved when the objects bounce up. Think about momentum. If two things crash into each other and you have to prove that the collision is elastic, you work out your kinetic energy before and kinetic energy after, and if it's equal, the collision is elastic. So it says, which of the following graph shows the total mechanical energy of the ball, how it changes with time? If the collision is elastic, you're not losing any energy during that crash. And we're ignoring air resistance, which means we're also not losing any energy because of air resistance. So my EMEC at the top must equal my EMEC at the bottom. But at the same time, my EMEC at the bottom after it hits is still going to equal to my EMEC before it hits. And that is only true because they say this one word, elastic collision. If the collision was not elastic, this would not be true. You would lose, obviously not lose, but you would turn some energy into heat or sound or whatever, so you wouldn't actually conserve your energy. So because it's elastic, we actually conserve the energy throughout the motion. There's never any energy loss, which is obviously a bit unrealistic, but we work with what we're given. So it is in fact option B. Option B, you see the EMAC doesn't change throughout. You could work out the EMAC at the highest point, you could work out the EMAC before it hits the ground, and that word elastic tells you the EMAC before it hits the ground is equal to the EMAC after it hits the ground, which would then still be the EMAC at the top. So during the entire motion, my mechanical energy is conserved because the collision is elastic and because there's no air resistance to take away any of the energy. Then question 4. Two cars are involved in an inelastic collision, head-on collision. Which of the following combination correctly describes the kinetic energy and the momentum, how it changes? So the total kinetic energy, if a collision is inelastic, it means the EK initial is not going to be equal to the EK final. So immediately it's only going to be option A or D. This can't be true. We know kinetic energy is not conserved during an inelastic collision. Then we look at the momentum. Is the momentum conserved during the crash? Well, the collision is inelastic, but no one ever said that the whole situation is not isolated. Okay, by that I mean no one is saying that there's friction or like an applied force or anything that is an external force that's going to affect the system. And if the system is isolated, in other words, there's no friction, there's no applied force, then my momentum is conserved. So that leaves us only with option A and D. We said the kinetic energy is not conserved and the momentum would be conserved because we always write momentum before is equal to momentum after. The only time we can't do that is when the crash is not isolated or the system is not isolated. There's friction and applied force, and no one has said anything about friction or applied force. So the total momentum must be conserved. So it's correct. 4A is the correct answer. Okay, then question 5. The question says the graph below shows the relationship between the power delivered by an engine of a car and the average speed of the car. So our job is, first of all, to figure out what can this graph possibly give us. Is it the gradient that we're looking at? Is it the area under the graph we're looking at, which would be half base times height? So let's start with gradient. So the change in power over the change in V, and its average velocity. Then you go to your data sheet and you try and see, is there a formula with P and V average in it? And if I manipulate it, can it look like this? And it is actually, it's P average is equal to force times V average. So if you take this and you divide it by V average on both sides, then you get force is equal to P average divided by V average. So it says the graph shows this relationship, the gradient, so they're actually doing it for us. They're asking us what the gradient represents. I'm not even going to look at the area under the graph. The gradient represents what? So we saw if we divide momentum by the average, power is a capital P, small p is momentum, and it did tell us power. If we divide power by the average velocity, we get force. So it's actually a nice one. It's option D. It's the applied force of the engine on the car. Question 6. A ball of mass m falling vertically downwards hits the floor with a speed of v and then bounces back up with a speed of 0.75 v. So 3/4 of the speed that it hit with, which makes more realistic sense. Something doesn't usually maintain its velocity when it hits the floor because some of the energy is lost in inverted commas or transferred into a different form. Okay, so be careful of these questions. They're quite common. What people generally do is they forget to assign a direction as positive and negative. So I'm going to make my original direction positive. I'm going to make my final direction negative. So when this object hits the floor, the velocity that it hits with is positive v, and the velocity that it bounces off with is negative 0.75 v. And literally take a pen and write that onto your question because it's easy to forget that. That is going to make a huge difference here when I sub it in. So they are asking which of the following combinations regarding the change in momentum is correct during the collision. So we go m, which was our mass, is equal, change in momentum is equal to m, Final velocity is negative 0.75 v. Initial velocity is just 1 v. You don't have to put the 1 there. I'm just putting it there. So negative 0.75 minus 1 times m. Okay, so minus minus. So minus 1.75. Sorry, we're not multiplying them. We're just saying minus 3/4 minus another 1. And it gives me minus 1.75 mv. But it also gives me that negative, which means that it's going the opposite direction. So that would be upwards. Remember, I assigned upwards as my negative direction. So then 1.75 mv, is that an option? Yes, it is. So it's option C. Then question 7, it says the base SI unit for the physical quantity work is the following. And then it gives you a whole bunch of options. So I'm looking for a formula that's got kgs, in other words, mass in it. And that looks like speed, possibly acceleration or something like that. So I'm looking for a formula that's got mass and velocity, or possibly mass and acceleration. Maybe we're going to have to do something to get those squares there. We're not sure yet. So my first instinct was to go this formula. Work is equal to force times delta x times cos theta. Now, obviously, we know that work should be measured in joules. But what they're saying is basically, what is an equivalent unit to a joule? Okay, so use a different formula and figure out what else could be a unit for joules, not like the proper unit joules, but what could be an equivalent unit for work. So this is not going to work because this has got Newton and meters in it, and that is not what they're looking for at all. So we need to think a little bit more. What other formulae do we have that have like mass and velocity or mass and acceleration? Okay, that is work or energy. Remember, work done is the same as energy transferred. So you're looking for either a work formula or an energy formula. So the only one I can think of is EK is equal to half mv squared, because that has got mass and speed in it. So I hope that covers the basis. So let's check. So a half of the mass, so let's just ignore the half here because we're just looking for the unit. So the unit for mass is kilograms in physics, and the unit for speed, now notice I'm not going to say divided by because it's times by speed. So the unit is meters per second, but squared. So put that in a bracket and square it, which gives me kilogram meters to the 2 seconds to the -2, which gives me option number C. Okay, so these questions, as all multiple choice questions, or most multiple choice questions, are not easy. Don't try and do them in your head. Write down, look for a formula that could help, or a relationship that could help, or look at a graph's gradients or area. It's not something you can just do at the top of your head, or very few of them are things that you could do off the top of your head. The next question, also quite a common one, says which of the following is the unit of measurement for the rate of change of momentum? Okay, so they're really complicating your life. So what is rate of change of momentum? Rate of anything means that's that quantity divided by time. So rate of change of momentum means change of momentum divided by time. So your job is to go to the data sheet and check, is there a formula you can manipulate that will look like this? And again, you've got this one. So if you divide by delta T on both sides, it's actually equal to force, which we saw earlier as well. So they're not asking what it equals, they say what is the unit of measurement for rates of change of momentum, and the unit for force is newtons. Then question 9, if the net work done on an object is negative, okay, or less than 0, then the kinetic energy of the object remains unchanged. No, that's not true. If the kinetic energy remains unchanged, according to the work energy theorem, in other words, if you're moving at a constant velocity, that's the only time it would happen. If you're moving at constant velocity, then your EK before, EK final minus EK initial will be the same. And in that case, you actually do 0 joules of work. So that's not what is happening here. They're asking, when do you have a negative sort of work? B, the kinetic energy is decreasing. C, kinetic energy of the object at the start is 0. In other words, it's like released from rest, or it starts from 0. And the kinetic energy of the object is increasing. Okay, this C is not it, because just because something's kinetic energy is 0 doesn't really describe much to us. It doesn't say whether it's going to go faster or slower or whatever. Something does negative work on an object when it's trying to slow the object down. or when it's it's a force pulling in the opposite direction, trying to make the object go slower. Work done by friction is always a negative because friction is always trying to slow you down. Work done by applied could be negative, it could also be positive, it depends. If you are pushing a box up a slope, and the box is actually moving up the slope, because obviously gravity is pulling it down. It's possible you could be pushing it, but in fact gravity is winning and it's managing to pull it down. But if you're pulling a box or pushing a box up a slope, then your direction of motion is in that direction, and your force applied is in that direction. So in other words, you are trying to speed the box up. You're not trying to slow it down. You're pushing in the direction of the force. So therefore, it would be positive work. However, if a box is being pushed up a slope or pulled up a slope, but gravity is so much bigger and it's winning, and it's actually managing to pull the box down the slope, then the box is trying to move down the slope and you're trying to slow it down by pulling it in the opposite direction, in which case work done by applied would actually end up being a negative. So to answer the question of when is work positive or negative, you need to ask yourself, is that force adding energy to the system and trying to speed it up, or is that force taking away energy from the system and trying to slow it down? So same thing with gravity, the work done by gravity. If you are moving, let's use a slope again. If you're moving down a slope, so your motion is down the slope, okay, then work done by FG parallel would be positive. And the reason for that is because your motion is down the slope, FG parallel is trying to pull you down the slope, so FG parallel is trying to speed you up. It's trying to move you along and speed you up, so therefore it would be positive. However, if your motion is up the slope, then gravity is trying to pull you down the slope, in which case it's trying to slow you down, in which case the FG parallel work would actually be a negative. So the right answer here is B, because whenever an object is being slowed down, then the kinetic energy will decrease. Okay, if that force is trying to decrease the kinetic energy or the speed, and therefore you'll end up with negative work. Question 10. Learners perform an experiment using identical trolleys, each of mass m. The trolleys are arranged as shown in the diagram below. They are initially at rest on a frictionless surface and are connected by a compressed massless spring. It says when the spring is released, it falls vertically down and the single trolley moves with the momentum p to the left. The magnitude of the momentum of the two trolleys moving to the right will be what? So it says that the momentum of trolley m will just be p, and then they're asking what is the momentum for the two trolleys together. Now you would think it's 2p because it's two masses, but law of conservation of momentum says that the momentum before the crash is equal to the momentum after the crash. And if the momentum of m is p, then the momentum of the 2m also needs to be p, but just negative p. Okay, but it does say magnitude, that's why there's no minus in front here. So you might be wondering, what does the 2m affect? Well, it will affect the acceleration afterwards, which is not the question. My momentum is conserved, and the momentum before the spring is released is 0, which means that the total momentum after the spring released also needs to be 0, which means that this has to be p and this has to be negative p for it to add up to 0 again at the end. So 10 is option B. Then question 11, a pendulum bob is released, which means the initial velocity is 0, from point P above a horizontal surface. At the lowest point Q of its swing, it collides with a stationary block situated on a frictionless horizontal surface. Which of the following combinations of conservation laws can be used to calculate the speed of Q immediately before and after colliding with the block? So remember, whenever you do a change in height, you're going to use energy. You're going to use Emec initial, or Emec at the top rather as Emec at the bottom. And whenever there's a collision, you're going to do sum of momentum before is equal to sum of momentum after. So they ask the speed of Q is going to be determined with energy, so that's A or C, and the speed of Q after the crash will be conservation of linear momentum, so that only leaves option A. Okay, next question is again a very common question. It's come up before. It says, which physical quantity is equal to the rate of change of momentum? Rate is something divided by time. Change in momentum Okay, so rate of change in momentum, and we know from the previous question was equal to force. The previous question just asked us for the unit. This one's asking what is it actually equal to. So it is C net force. Then question 13, it says two trolleys X and Y of masses M and 2M respectively are held together by a compressed spring. Initially they are stationary on a horizontal floor. Then it says the spring is now released and it falls to the floor and the trolleys move apart. The magnitude of momentum of X while it moves away is, and then they compare it to Y's momentum. So it can't be zero. That would mean that it would be stationary after the trolleys is released. Okay, the magnitude just means that you don't have to factor in the negative. So if the momentum was, let's say, P, or negative P rather, then the answers on the memo would just say P. So magnitude just means just ignore the negative. So it is option D, and the reason is the momentum of X is equal as the momentum of Y, because remember that initially they're standing still. So the sum of the momentum initial is 0, which means the sum of the momentum after, if we use law of conservation of momentum, needs to be the same. So it needs to be 0 after as well. So if the momentum of X is P in this direction, the momentum of Y would have to be negative P, but in the opposite direction, so that when you add them together, it ends up giving you 0 again, which is the same as the initial momentum. Then question 14 says an object is dropped from rest. After falling a distance x, it has a momentum of p, ignore air friction. The momentum of the object after it's fallen a distance 2x is, and then they give you options. So we're looking at momentum, we're looking at distance. Okay, momentum is, first of all, P is equal to M times V. So the mass of the object is not changing, whether it falls a distance x or 2x, so we're not going to worry about that. So it must be the velocity that we need to look at. So we're going to try and see how does the velocity get affected if an object falls a distance 2x instead of x. So we've got a formula in that's got velocity and distance in. So we've got v final squared is equal to v initial squared plus 2g delta x. Okay, we know that the object falls from rest, so v initial is actually 0. So v final is equal to 2g delta x, sorry, v final squared. Okay, so if we square root this to get rid of the square, we have to do the same on that side. So v final is 2g delta x all under square root, okay, which would we then sub into there. So it would be m times square root 2g delta x, but like I said, m stays constant throughout the sum. If the distance now doubles, we go v final squared. The initial velocity is still 0. It's still falling from rest. And it's plus 2g, 2x. Now we want to make this look similar to that so we can relate the two to each other. So I'm going to take the 2 out and make it 2g delta x so that this looks the same, or rather this one looks the same as this. Okay, we're still going to square root it. So we square root, okay, and then we'll take that square root 2 out like that, and then it's 2g delta x. Okay, now we know that square root 2g delta x was the original velocity after a fall at a distance x. So that's my initial momentum. So that means that this is square root 2 times p, which was the initial momentum, so that gives me option B. Then question 15, a block slides across a rough horizontal surface. The work done by friction changes what of the following energies? So work done by friction is obviously going to slow down the object, so it's going to affect the kinetic energy of the object, and it's going to affect the internal energy of the system. So that is option C. Then question 16, an object of mass m traveling at a speed of v along a straight line collides head-on with the wall. Assume that the collision is elastic and the object rebounds in the opposite direction. If a collision is elastic, that means that no energy is lost when the object hits the wall. So it hits with the speed of v, meaning it's going to rebound with the speed of v. But just be careful. If it rebounds with the speed of v or in the opposite direction, we need to make one direction positive and one direction negative. And they know you are going to forget to make one direction negative, so they're going to put an option in there that is going to look like your answer if you forgot that. So careful of that to try and catch you. So it says, what are the changes in momentum and in the kinetic energy of the object as a result of the collision? So the change in momentum of the object would be, okay, so m staying constant, final velocity is negative v, careful, and the initial velocity is just v, so it's negative mv minus another mv, which gives me negative 2 mv. Okay, that's the negative is not an option, so they're obviously looking for the magnitude. So the only one it could be is C. Let's just double check the change in kinetic energy. Okay, if the object has the same speed going towards the wall and away from the wall, when you work out half mv squared, because v is the same for both, remember energy is also scalar, so the negative isn't even factored in. The energy going towards the wall might be 20 joules and the energy going away might be 20, whatever the value is, but it's ultimately going to cancel out and just give me naught. So 16's answer is C. Then question 17, ball P and Q of the same mass are dropped onto a concrete floor. Both balls hit the floor with the same speed v, so their initial velocity is v. Ball P rebounds with the same vertical v, which means that the collision must be elastic, but Q rebounds at the speed of half v. Refer to the diagram and ignore air resistance. And then they ask you which of the following statements regarding the collision of each ball with the concrete floor is correct. So A, kinetic energy is conserved for P and Q. Now that's a definite no, because Q loses speed as it rebounds, so it cannot possibly conserve the kinetic energy. B, the change in momentum of ball P is greater than that of ball Q. Well, let's work that out. Change in momentum is mv final minus initial. So I've subbed in the initial. Again, please be careful of that negative when you change direction. Okay, assign one direction is positive and one is negative. So my change in momentum here gives me negative 2 mv for P. However, for Q, the change in momentum gives me only m times half v minus v. So half v minus v gives me a negative v times the m, so negative half mv, so therefore it is option B. The change in momentum of P is greater than the change in momentum in Q if you compare the two values with each other. Then question 18, if the net work done on an object is positive, then we can conclude what about the kinetic energy of the object. Okay, so just recapping again, if work done is positive, it means that that specific work, let's say it's work applied, is trying to speed up the object. If work done is negative, it's an object, the force is trying to slow down the object. So if they say that the net work is positive, then overall, the forces are trying to speed up the object. So the kinetic energy has to be increasing. If it was decreasing, then the work would be a negative. Then, question 19, a very standard sort of impulse question. An airbag can protect the driver from serious injury during collision. Same sort of questions with crumple zones. Which of the following best explains why this is possible? Okay, so if there's an airbag or a crumple zone, it causes an increase in the time it takes for the object to stop. Okay, because that front of the car crumples in a little bit, so the car doesn't come to a dead stop in a split second. It takes a bit of time for that crumple zone to squish in, so the impact time therefore increases. And then you look at this formula, okay, let's just manipulate it. So force is equal to change in momentum over change in time, Newton's second law in terms of momentum. If your impact time increases, okay, these two are inversely proportional, then the force on the object would decrease. So question 19, the impact time increases and the net force decreases, so it's option C. Then question 20. The last question says a vehicle of mass m is moving horizontally at a constant velocity on a frictionless path. The kinetic energy of the vehicle is k and the momentum is p. The velocity of the vehicle can be given as k, and then they give you a whole bunch of options. So it's moving at a constant velocity, the momentum is given, the ek symbol is given, and we have to figure out which of these is true. Okay, with these sort of questions, I find it easiest to go through each of them and sub in. So ek is half mv squared and momentum is m times v. If I simplify this, okay, it ends up giving me half of v. And that's not what they want. They want half of the velocity, they want the total velocity. So that's not an option. B is 2 times the kinetic over momentum, 2 times kinetic energy, so 2 times half mv squared, half mv squared. over the momentum, which is m times v. Okay, if I go 2 times a half, that actually gives me 1. So at the top we get a 1. Okay, then m times v squared over mv. The squared cancels out with the v there, the m cancels out with the m, the 1 is just there as a placeholder, so we're just left with v, so it is in fact option